All right, so hi everyone, thanks for coming, and it's kind of nice to have a smaller number of students because we can get to interact a little bit more, and it's more interesting for you. However, the counterpart of it is that the others won't be seeing the same lecture. I mean, won't be having the face-to-face lecture. And you'll be alternating. So I guess next week you won't be here. It's the even number, I think, something like that. I've never understood the system, but anyways, we will learn to deal with it on the fly. All right, that being said, I am recognizing some faces from last time. Hence, my first question, who can remind me of the things that we tackled together in our very first lecture? Hey. So real-time embedded what? This is the name of the course. Who can do better? Not bad. Yeah? Huh? Constraints. Oh, awesome. Yeah, definitely. So one of the things that we talked about are the constraints when it comes to the real-time embedded systems, that's for sure. And we've definitely talked about how the literature segregates the real-time systems into how many? 3, 4? All right. Me personally, I would go for the 3 because to me, the weakly hard and the hard real-time system have the same constraints. All right. So basically, there are subgroups in that category. However, one can argue that it could be 4, but then again, I would accept an answer like that, but you need to explain why. All right? Personally, I would go for the 3. Stop. Okay. So the V cycle process, it looks like the letter V, and it's usually follow-up. It's extremely important for you, for your own good for later on. We have an descending phase, and we have an ascending phase. All right. So usually it's divided into three different parts. I have chalk, but it would be extremely complicated. Nothing here works. Oh yes, perfect. Finally, not for you guys, but. So here it goes down, and here it goes up, right? We have 3 different steps in the descending part of the V cycle. Can anyone guess what those are? They look something like that. All right. So here we have what we call the black box. So we have a set of inputs and a set of outputs and an expected behavior. We don't know the details of what's going on in there. So this is the big picture functionality of the system. All the way down here, we have something that we call the white box. So here we have every single detail of the implementation, and this is down the descending part of the V cycle. What do we have in between white and so the gray box? And this is where we have a halfway through details. This is to create the smallest units. This is to integrate, the smallest units, and this is to integrate the whole system. So this is down the V cycle. Question in the back. Question. I have this going down, this aspect. Now coming up, what should I be having here? Do you have any idea? It's a wild guess. I'm not expecting you to know it. So development process, white box what I'm black box what I'm expecting from a macro point of view, zoomed out, extremely zoomed in down the hill, and what should I have here in order to make sure that's working correctly? The test. Thank you so much. Who said it? Perfect, man. I remember you. All right. So here, for each micro unit, we have what we call the unit tests to make sure that individually each unit is working correctly. What is the second step up the V aspect of the cycle? So if we have integration, we should have some integration tasks. Here we can federate, gather together the smallest units and make sure that they're still correctly behaving. And then the last step is not to look, not to check the details anymore, just to apply some input and see if the output is what I'm expecting. The beginning of your career, you'll be here. And you'll climb up this ladder, should you choose a technical domain. Fair enough? Yeah? Speak up, please, so I can understand, and I would repeat your question as well. The white box is where the development process is kicked off. Yes, this is the development process. No, the black box is where you start. You need to have the skeleton of it, all right? And then you dispatch it into smaller groups, all right? So all this is considered to be the development process. Yes, I could. So imagine that I need to implement some driving aids. Aids, help, driver assistance. So basically what I do is I need to list the inputs that I'm doing and the outputs that I'm expecting. This is not fully part of the requirement. This is the interface between the development process and the requirement, because you're extremely close to the actual implementation. Your final product, implemented product, will be here, but it starts here as a skeleton. So imagine that your driving aids is made out of 3 functions. So here you will have 3 big functions. You'll have to specify the inputs of those functions and the outputs. All right? Just design that. Yeah, just designing in order to be able to fill in the skeleton here. All right? Yeah. This is the last question because this is not a project management course, but I mean, it's extremely interesting for you to know it, to be closer to the industry. Yeah. Now, this is generally something that you should know of. There are new practices and old practices. Usually in the industry, people resist change, meaning that if they're used to some kind of process, they follow. If you come up, you're freshly graduate and you're so happy about your new process, okay kiddo, stay in your corner. Get it? So there's the there's the ideas, and then there's being pragmatic and seeing what's happening in real life. This is what I did when I used to work at Renault. And this dates back from the 70s, something like that. As long as it works, don't change it. More questions, if you can ask them informally later on. Or during the bike project that we're working on. All right. All right, so let us have some fun. A big question for everyone that is here today. So embedded systems, are they software or hardware? Definitely both. Today, was it the case 30 years ago? So the case 30 years ago, it was closer to the hardware border here, And then throughout time, it shifted the interest and the added value shifted towards the software. How come? Back in the days, the innovation was hardware oriented. Today, the innovation is software oriented. How come? Yeah? More complex, yeah, definitely. So we're trying to avoid having complex units, definitely. What? Who else? I like her. So we've reached something that is satisfying enough, and we say that my hardware like that, it's fine. Now let me try and do something more agile. Software, I can change it as many times as I want, right? And make the best use of the hardware that already exists. Get it? So this is why you're going to hit the job market with your friend. For instance, if you go and at Valeo, a lot of stuff are embedded software. Most of the functionalities, if not all, are strictly provided by the software that you have. The added value is the software itself. All right? This doesn't mean that we need to undermine the hardware that is beneath it. Because we've seen in what course that, wake him up. Behind you, wake him up. We've seen in what courses that there are different layers. In what courses we've seen the different layers and the connection between the hardware and the software? OS and CA. So you know that there's some hardware that we're managing beneath the software. All right? Mais pourquoi il me fait lui? Okay. All right. So here where the fun starts. Any South Park fans here? You are? Have you seen this episode? Do you remember? It's a funny thing. It's interesting actually to check it. They are extremely noir, dark humor, but it's so funny. And these are called the member berries. So they try to remind you of the good old days. And what I'm trying to point out here is things that you've learned in a couple of courses, such as what? I mean, check the list. You've seen FPGAs before in DSD, and you've seen microprocessors, both in CA and OS. We've talked about them. Are you familiar, who's among you familiar with the term microcontroller now? You are? You're not really sure? Hold on. I'm just asking who is familiar with it. I didn't say give me a definition. You are confident enough? Who else? No? Okay. PMUs, definitely no one's seen it before. No? Any DMET here? I don't have DMETs. That's so weird. ASIC. Did you talk about it in the DSD? The other group told me that I talked about it. Did I? I did? Must be the age. Go ahead. First you, because you're pretty sure, then I'm going to go for her. Yeah. You. Microcontroller. Shh. What is a microcontroller? Shh. Go ahead. Interesting. Signals, okay, why not? I mean, signals. What do you mean by signals? I think that you have an idea, but you're not pretty sure as well. Can you give me an example of a microcontroller if you cannot define it? Huh? Arduino, fancy. You're gonna be shocked. Today you'll be learning something new. I'm not surprised that you gave me this answer, but today, because you're a future engineer, you're gonna know how to precisely define a microcontroller and know what exactly an Arduino is. Give it a shot. You told me that you know microcontrollers, so what can you tell me about them?
I know that it can, it's part of software, it can handle software and handle hardware at the same time. An example of it is Raspberry Pi and Arduino. I have the same answer.
Okay.
And I think, although there are some
why wouldn't I don't know, an FPGA be connected to the internet? Yeah? We're gonna get to that. We're gonna get to that. Shh. A microcontroller is? Yeah, you definitely could have put a program on it, definitely. Alright. So it is the brains to control a lot of stuff. Interesting answers here. However, if that's the case, what would be the difference between a microcontroller and a microprocessor? Because you can also put some instructions on it, and it could also be the brains of a system. Huh? AVR? Where did you learn this word? Okay. So you said AVR is too much for them. They're going to see it later on. So keep it to yourself. What do you have?
Microcontrollers can have some kind of processing skills, but not all processors are.
Skills? Okay. Oh, interesting. Not all processors are microcontrollers. This is what you're trying to say? Interesting. Yeah? One last time. Yeah? Who has what? We have a winner, ladies and gents. All right. So usually speaking, a microprocessor is a standalone CPU. Do you remember the name CPU from last year? You don't? What does it mean? Central processing unit. So it's the processing unit, right? Usually, so if you remember quite well your CA after the exam, of course, why would you remember? If you remember quite well your CA and OS, in order to a computer to work correctly and to provide something, the CPU is not enough. It needs to deal with other modules. What are those modules? Memory, definitely. To do what? Why the memory? To get the instructions from and the data. What else? I/O modules. At least those. All right? So you can go ahead and buy a microprocessor. It's not useful if you don't connect it to a memory because it won't get its instructions, and plus it connect with the environment, whatever that environment is. Could be a keyboard, mouse, screen, whatever. Just keep it down. All right? You'll need some I/O module. Unlike a microcontroller, a microcontroller, it's a whole package. It has a CPU, an I/O module, and a memory, all in one. So it has a huge advantage, but it has a disadvantage as well. Yes? Come again? System on chip? You can consider that. It's not a problem. I mean, it's not really problematic here. We can have a debate on it. Yeah? The microprocessor would never work without a memory and without I/O modules. The microprocessor is a chip, and it cannot work alone because it needs memory to get the instructions from and memory to deal with the data. No, wrong. Because if you, so let me give you an example. If you open your desktop computer, right, you're going to see a motherboard. On the motherboard, you're going to see a microprocessor, right? And you're going to see some RAMs, and you're going to see some I/O modules, all right? Unlike a microcontroller, and you have never seen a microcontroller till now. Some of you seen it, but they don't know that they've seen a microcontroller, all right? So it's on its own. If it doesn't belong to a bigger family, it wouldn't be functional. So we said that this is one advantage of the microcontroller over the microprocessor. Now my question is, what is normally a disadvantage of microcontrollers versus microprocessors? Huh? Definitely more expensive. Yes, I'll give you that. Why? Because it has some more processing power. Usually microprocessors have more processing power than the CPU units inside the microcontroller. That's one. Second of all, she said something interesting. What was that? You said something interesting. What do you mean you can adjust the memory? I'm curious about that. Oh, yeah. Right, so in the microcontroller, everything is graved in a way or another. You cannot change the memory of it. Unlike you could, for instance, with a microprocessor on your motherboard, you can add extra RAMs. You cannot do that in a microcontroller. Awesome, perfect. You got the concept. All right, so usually it's the computational power, usually it's the cost, etc., etc. What would be the heart of an embedded system, generally speaking? Microcontroller. Because it's extremely small and it's a whole package, so it's quite interesting. Right, we're going to discover the PMUs and the different things throughout those upcoming slides. Let me start with the PMU. So systematically, whenever I tell you PMU, you should think, the first thing that you need to think of is what? Power management. All right? It's a power management unit on a board. On a motherboard, on an FPGA board, on a microcontroller board, right? So basically it is something that you can find on whenever you're gonna have the green thing, the green board, right? You might see it there, you might. Its role is primarily to deliver the exact voltage and to make sure that module 1, are you ready? Yes, I'm ready. Module 2, are you ready? Yes, I'm ready. So here's some voltage. Everyone is ready? So let's make the whole system work. All right? It's some kind of le chef d'orchestre. The maestro, they told me that. Yes. The maestro of the whole board when it comes to voltage. All right? Let me jump to the third sentence. In the back, talkative guy in blue, stand up. Yeah, you. No, him, next to the girl, stand up. You, man, you, yeah. All right, third sentence, third point. Third point. What's over voltage? Oh, awesome. Over voltage is more voltage. Why is that bad for a board? It will barbecue it, definitely. It will burn it. And it happens a lot of time to a lot of people. I am thinking of them. I think you've burned something 2 years ago. I think so. In the GSD, definitely. All right. So over voltage is so obvious. What about under voltage? And why would it be dangerous? Shh. This is finesse. Perfect, man. You did it in finesse. You can sit down and stop bothering her. Or she bothering you, I don't know. We're for the parity. Over voltage is so obvious. I don't want to barbecue my, my board. Under voltage, remember we're dealing with electronic components. So they deal with bits, ones and zeros. How do they interpret the ones and the zeros? To the components, it's either, let's say, 0 volt or 5 volts, let's say, all right? So imagine that you want to represent to 1, but you have under voltage, so you're unable to go past 2.5 volts. What would happen? The component will go bananas because it's seeing 2.5, so it's neither a 0, neither a 1, so it can misbehave in so many ways. Best case scenario. Worst case scenario, I'm going to keep it to myself. Fair enough? If we're dealing with different sources of voltage, external voltages, so basically it can handle it as well. It can give some extra general purpose input outputs, slots, and something that you've seen in GSD, next to GPIO. So GPIO, general purpose input outputs. And ADC, so what? Analog to digital converters. So we can have some extra stuff. And usually we can control it, you know, in order to make sure that it's doing its task and communicate with it. And we're going to talk about communication protocols in embedded systems later on throughout this course. Guys, everyone pay attention to the last point, to the last bullet point. What does it say? It's not mandatory. What does it mean? The PMU, so the power management unit, is not mandatory. What does it mean? It's not necessarily there on all boards. Why? Something that is so beautiful and gives so many good features, why wouldn't it be on a board? Yes. It costs a lot of fulus. Any extra 50 cents that you save is more money to the CEO. Boards such as RASP, those who have already seen a Raspberry Pi, you can recognize the logo here, but you cannot recognize the logo that is next to it. So the British, the UK people created the Raspberry Pi, and some other country created a nice copy of it and called it an Orange Pi. Which country is that? It's a riddle. And there you can also find something called the Banana Pi, by the way, by the same country. Come in? Yeah. What? It is. It's a is it considered a microcontroller? It doesn't have a memory. It doesn't have a thing. No. But it's a controller in the sense of it controls the power, right? But it's not a microcontroller in the sense of CPU and processing, etc., etc. Right? Everyone knows the PMU now. Okay. Yeah? General purpose input output. So it's okay. These are channels that you can use in order to communicate with the external world. So you can hook things to it. You can connect things to it. Right? General purpose input outputs. So they can use for so many different reasons. It gives you extra stuff. It's like extra legs or something like that. All right. So let me choose wisely now. Who am I going to choose? His friend. You're sitting next to him, so I assume you're friend. Choose your victim. Go ahead. You don't want to choose. So next in line. Check this out. Anyway. All right. For your own info, this is a real life. A picture of a real life PMU, all right? And you can find so many on the net. All right, ASIC. How much time do I still have? I'm supposed to finish at what time? Right, so approximately 35 minutes. All right, so let's see. Someone who remembers DSD. Who remembers the things that I've talked about in DSD? No one? You do? Okay. So what's so special about ASIC? Not general. Okay. All right. All right. So if we compare them to the FPGA, let's say, the FPGAs are usually reprogrammable. So basically, you can synthesize different hardware on the FPGA. Here, you do it once, and that's it. They're specific to a particular application or customer or whatever. Why is that? Why bother tailoring something that is extremely restrictive and specific to a particular application? Performance. Thank you so much. I like you. I like you. It's definitely to optimize energy consumption, performance, etc. Because when it comes to computation, performance is key. What is performance in computation? Time, more precisely, execution time. All right. So optimize power and performance. Now my question to you is, think about an industry where this particular type of systems, so ASICs, right, are used, and why? Think about it. So imagine in what domain something that is not reprogrammable is extremely beneficial, because if it were reprogrammable, we could have a lot of issues. Yeah. Domain. Huh? Cars, motors, domain, again, one more time. So cars, automotive industry, why? You could have some ASIC in cars, but usually they're not purely ASIC, usually. But you could definitely. Who said it? You're not that far. Why airplanes? Sure, okay, so if we look at it from a performance-wise, but remember my question was so precise. Why would we use something that is not reprogrammable? Who said to prevent errors? The errors would stem from where? Impossible, because again, if you have something wrong with the logic of the ASIC itself, it will propagate the human error. It's not about the human error. Yeah, in the back. Okay, so you're still not naming domains. Industries. Who said it? Spaceships. Okay, space shuttles, definitely. In airspace industry. Why? Let's see. I'm gonna remind you of your name, Abdurrahman. I'm gonna send Abdurrahman to the moon during daytime. Doesn't really change a thing, all right? Once you leave the ozone layer, what would happen? Exposed to what? Imagine you're wearing a face mask, an oxygen mask. Sun waves? Okay, use another term. Radiation, who said it? Correct. So basically, if you send electronics in space, they're subject to radiation, extreme dosage of radiation. So let's see, if we use an FPGA that is by nature reprogrammable, the FPGA will say that someone is trying to reprogram me, so let's do that. If an ASIC is feeling that someone is trying to reprogram them, right? I'm not supposed to do that, right? So I'm going to say, hold on, there's some kind of error happening here. So I can act on the error in order for it not to become a failure. So it can better resist radiation because it knows by nature it's not reprogrammable. So you cannot alter what it's supposed to do. All right? So we say that it's radiation tolerant. And the one who said cars, you're not completely wrong, because sometimes with the vibration of the cars and the frequencies, you can alter some stuff. This is why we have a lot of fault tolerance and some resilience mechanism. But in space, you have no idea about the amount of the radiation that is out there. All right, learning a lot of stuff. Interesting. This is your baby. You should know it by heart. You fed it, you you fiddled with it, you created a lot of stuff with it 2 years ago. Do you even remember FPGAs? So you used an FPGA, it was a big board. Am I saying correct things right now? I am. Where, The thing that you hold between your hands is the FPGA board. It's a board that has an FPGA on it. The FPGA looks something like that. What was the name of the FPGA unit on your board 2 years ago? I personally don't remember anymore. Do you? Huh? You don't? Was it the Max 10 or something like that? So what's so special about FPGA? Reprogram, resynthesize, you can prototype, make errors, do stuff, doesn't work, lose your mind, then go back to it, and you know. So yeah, what kind of language do we use in order to create this hardware that will be on the FPGA? So hardware description language, I'm gonna get there. And precisely what language did you use? VHDL. Awesome. So an FPGA could be seen as a whiteboard on which you're gonna draw some hardware, and it will work. It should. Make sense? Perfect. Can you change the hardware or add extra hardware to it? Definitely yes. FPGA, by nature, you can reprogram it. So yeah, definitely. It's a whiteboard, you can draw whatever on it. You can wipe it off and then write other things. All right, this is useful where? In airspace? No. Where? Whenever you're gonna have a lot of prototyping and create proof of concepts, etc. Have you ever heard the word POC before, proof of concept? Right, so when you create some so when you create a system that proves the thing that you're trying to implement, and then you can go ahead and massively produce it. All right. So it's extremely interesting while you're in the development process, or when you're trying prototype number 1, prototype number 2, etc., etc. All right. Check this out. In your next tutorial, have you done the first tutorial yet? By raise of hands here. That's it. Anyway, in your next tutorial, I'm going to give you just a quick summary of it. You're going to use the FPGA one more time, and this is the only time they're going to use it this year. On the FPGA, you're going to create some hardware. Make sense? This is, you know this from the DSD course. You already know this from the DSD course. However, according to the things that you've learned today with me, you know that the hardware itself, it should have something else running on it in order to implement some new innovation or functionality. What is it? So every hardware should have a software. So the thing that you're gonna do in your tutorial, you're gonna use the FPGA as a whiteboard, create a processor on it, and on that processor, you're gonna create a software that will run on it. No, create, because remember, you didn't simulate in DSD. You created stuff. You created stuff. Question: how much time does it take to create a processor? Can we count it in minutes, in hours, in days, in years? All right. So the good thing is you're not going to create the hardware that will run on the FPGA. You're going to use some intellectual property blocks already there, and it's called the NIOS 2 processor. It's a soft processor. It's a soft processor coded in HDL, in VHDL. Then you're going to synthesize it on the FPGA board and use it. Very beautiful. The thing that you're going to do is you're going to implement a extremely small software that will control the switch, the LEDs using switches on the FPGA. It should be fun. Should be. All right, and this is the final thing that we'll be seeing together today, to stay synchronized with the first group. It will take a lot of time. So by raise of hands, who've seen the picture to the right here before? Higher so I can see. Awesome. Can anyone tell me what is the name of the board I'm showing you? It's an Arduino Uno board. Awesome. Are there other Arduino boards out there? Mega, for instance. Oh, awesome. Perfect. All right, let's play a game. Who's ready to play? No, you already played. You want to play a game? All right. Stand up. So here we have a board with somewhat good resolution, all right? So we can see stuff on it. Can you confirm in the back? You're going next. Focus. No, you. Now you're seeing an Arduino Uno board, and I have a list of components that I want to identify on the board. Make sense? List of components I'm trying to identify on the board. So the first components I'm looking for are the LEDs, the LEDs. Can you see the LEDs on the board? Usually the different components have this, they have a small name or a small tag next to them. So you can just tell me the tag and I will see it. If there's no tag, this is not your component. Anyone? You have a seat. Have a seat. It's fine. It's easier. Have a seat. Now you. Anyone else? Can you see the lads? Okay. Say a letter or a name. TXRX. Correct. Stop. TXRX. They are in the middle on the board next to the Arduino here. I'm saying that for the people online. All right, so here, can anyone guess what is meant by TX and RX? Classy. So TX stands for transmission, and RX stands for reception or receiving. Usually, let me explain it first. So TX, whenever this one flickers, this means that your board is sending a stream of bits to the outside world. On the other hand, the RX would be the getting a stream of bytes or bits from the outside world. So usually, most boards, if not all, motherboards, network cards, etc., they have LEDs indicating that something's going on in there. So if you look at the back of your desktop computer, for instance, you're going to see some network card with some flickering light. This is to show you that something is being sent or received. All right? So get familiar with those tags. You're going to see them a lot later on in your life. All right. Who else? Everyone got that? Right. Who else can see something? Another LED here. Huh? Here? All right. So here, right next to the top edge of the, under the top edge of the board, we have a LED called L. This particular LED, on some boards, they have a debug LED. Why would it be useful to have a debug LED? Yeah. But why bother putting it on the board itself? Because you might not have a LED, so you can connect it to some output pins, let's say. So basically, you can use that LED that is usually physically connected to one of the output pins. In this case, in the Arduino Uno case, can anyone guess to what pin it's connected? Yes, 13. It's the closest one to it. Perfect. All right. So this is a debug LED. I have more LEDs. The on-lag LED that is next to the Uno word on the board. And this is useful for Seeing if the board is under voltage or not. Under as in, is it connected to some power source or not? All right, fair enough. All right, so these are the LEDs that we have here. All right. Next. Are you still up to the challenge? Or do you want me to try some? No, she doesn't want. All right. By show of hands, I want to see again the people who already seen an Arduino board before. Okay. Where's the clock on this board? You don't remember or you don't know? You don't remember. So you knew that. You know that, but you don't remember it anymore. Who else can, anyone can tell me where's the clock? There's a clock here. Anyone can guess where it is? I'm not expecting anyone to know it. It would be great if you know it, but. Yeah. Circle. Circle? The oval shape here? This one? You got it right. Perfect. So here, please take notes, of course. If not, you're not taking already. No. Usually boards, they have external clocks on them. What for? To synchronize the timing of every module that might be on the board. All right? The type of this particular clock that you're seeing here, we say that it's crystal based. Anyone has an idea what that is and why would we have a crystal based clock? Perfect. So crystal based, it means it uses quartz. Have you ever heard the word quartz before? If you have watches, sometimes you can read quartz on them. It's an element, it's a physical element naturally found in nature, that you can find in nature, and it has a particular interesting property for physicians and electricians. I'm so tired right now. All right, so it vibrates. On a microscopic scale, of course, you don't see it move. It doesn't make any sense. All right, so the vibration is steady and it allows us to create impulses. So rising edges and falling edges. This is perfect to have a clock on its own. All right? This is not the only clock that we can find on this board. So this is where I'm honing your engineering skills. Try to notice something here. All right, before I get to that, let's find the microcontroller first. So the MCU is the microcontroller. First off, anyone can guess where is the microcontroller on this board? Yeah, go ahead. The unit above the clock. Who can say something more interesting? Keep that thought. It is that rectangle, black rectangle right here, this die. Well, you are both right. We have two microcontrollers on this board. The main one is the big one, rectangular one, and then we have a smaller one, a square one, right above the clock. The main one is the one that you actually get to program and work with. This one is used for something else. We're going to discover that in the upcoming lectures. Now, I'm leading you somewhere. You can notice that this particular clock is extremely near that microcontroller, the small squared microcontroller. Where would be the second clock? Shh. The second clock. So it should be not far from the second microcontroller or the main microcontroller. It's that small one that is right above it. And this is not a clock per se, it's called a resonator. A ceramic resonator. It's out of the scope of this particular course to talk about the comparison of the two, but the big one is costlier. That one is inexpensive and shadier. All right? 2 clocks. Ready to be more surprised? These are not the only clocks on the board. Remember what you learned today. Yeah. Inside the what? Inside the USB. Of course not. It's inside something, all right, but not the USB. Inside the microcontrollers. Because remember, a microcontroller is the package. Inside it, you have a lot of stuff going on. Memory, I/O modules, and you have an internal clock. Wonderful. Question. Why would I need an external clock if my system, my microcontroller already has one? Yeah, in what sense? So synchronization. Okay. It of course has to do with the real-time constraints, that's for sure. But now remember the very first tutorial in your CA course. The more instructions you're executing and the more cycles you're getting into, what would happen to the whole system? It will speed up, right? It's speeding up. And doing that, it will heat. And heating and overheating affect the internal clock in there. So it gets desynchronized. It might get desynchronized. So for safety measures, of course, because remember embedded systems, and we might be dealing with hard real time or at least weakly hard. So basically, we need to guarantee the synchronization. We're going to discover that in the very next lecture. We're going to see a beautiful schematic of the insides of the microcontroller. All right, I'm not done yet. Can you talk about the miscellaneous stuff? So he said USB here, and everyone can see the USB. Anyone can guess what's that in the bottom left? That's a power supply. Can anyone guess what do we have here to the right, upright of the main microcontroller? Those are, anyone? Okay, so those are communication pins, so we can use them to communicate with the microcontroller. We're gonna get to that later throughout the lecture, the course. And one last thing, you need to have some voltage control. So you have a regulator here. Do I have a power management unit on that particular Arduino board? Doesn't seem so. All right. One of the last things that I'm showing you before you leave, I'm telling you the name of that small microcontroller here, and it's called the Atmega 16U2. Not done yet. I said before you leave. Once I'm done. So, all right. Can anyone guess the name of that, the big one, the main one? Come again? All right, so one of your colleagues from the first group today, they told me Atmega 16U1. It's extremely interesting because, yeah, it could make sense. However, it's not that. They started correctly, it's Atmega, but then we're going to see that there's a difference with the suffix here. So the same prefix but different suffix, and we're going to discover why they're named this way. Any questions? You good? All right, thanks for coming. See you next time.